number 13 in a series for TEAS preparation. I want to give you all the information you're going to need to uh, adequately address questions concerning acids and bases. And all these other terms are directly related to acids and bases. All right, let me share my slide set. Here we go. And there. Okay. A little history. Little history never hurt anybody. The first attempt to chemically describe an acid and a base was proposed by Arrhenius, a Swedish chemist, in 1884. And Arrhenius said in his investigations that the acid nature of a solution was based upon the um, ability of a compound to release hydrogen into solution. So we would say a generic expression with that would be this, and A could be anything. It could be, in this case, nitrate, it could be chloride, it could be sulfate, but that's your generic acid. And he said what happens is that hydrogen ionizes in solution and leaves behind the rest of the molecule. And notice that 1 plus and 1 minus is neutral, right? They balance. He also said that bases are those compounds that have, let's see, let's use MOH. It's always a metal or something in the metal position. And it produces hydroxyl ions. That's a polyatomic ion with just one oxygen, one hydrogen, and a negative charge. That was the definition proposed by Arrhenius. And this works for probably 90% of the acids and bases that we'll encounter. The problem with that idea is that it was noticed by some, even Arrhenius himself, eventually, that you could have a basic solution from a compound dissolved in water that did not contain a hydroxyl group in its formula. The perfect example is ammonia. Right? Ammonia in solution produces hydroxyls. The question then is, where'd they come from? Well, it was up to a Danish chemist and an English chemist. They worked separately, and they came up with the solution about the same time. So they're both given credit for this definition of an acid versus a base. What we see is that in aqueous solution, water is a reactant. Ammonia reacts with water, and a proton is transferred from that water molecule to that ammonia. And that gives you the ammonium ion and the hydroxyl ion. So Bronsted and Lowry proposed that rather than look at it in terms of what's in the molecule to start with, necessarily, but look at it in terms of protons only. Protons, and I mean protons is that, right? Right? There's a hydrogen atom. Most of them are that way. We don't have a neutron in this one. But when you remove the electron, what do you have left? A proton. So when I say hydrogen ion, a positive hydrogen ion, or a proton, I mean the same thing. So Bronsted and Lowry proposed that an acid is a proton donor, right? And virtually all acids will do like this. Like hydrochloric acid will donate a proton to something. So if you put it in an aqueous solution, what does it do? It donates a proton to water and leaves behind the chloride ion and this polyatomic ion called a hydronium ion. That means that this is the acid, and by their definition, water is a base. A base is a proton acceptor, right? So hydroxyl ions will accept protons, water molecules will accept protons, um, ammonia molecules will accept protons and make ammonium ions. So their definition encompasses all of Sorensen's acids and bases plus more. Oops. Okay. So definitions. When we have an acid and a base reacting together, in this case, the acid is hydrofluoric and the base is water. Water is the proton acceptor. Hydrofluoric acid is the proton donor. You always get as products a conjugate acid derived from the reactant base. So water now becomes able to donate a proton because we've added a proton to water to make the hydronium ion. Now you have available for proton donation from the conjugate acid. On the flip side, the acid, hydrofluoric acid, donates a proton. Now it produces a fluoride ion, which is able to accept a proton. So acids produce conjugate bases, bases produce conjugate acids. There are some compounds that um, in chemical reactions can behave as either an acid or a base by the Bronsted-Lowry definition. Water is one of those. Water can either donate a proton or it can accept a proton. And that's called an amphiprotic substance or amphoteric. They're interchangeable terms. Now, when we talk about, we can classify acids in terms of how many protons that each molecule can donate, right? If there's only one proton available, like this one, or like this one, uh, right? Or like this one, right? Notice the proton always comes first. The hydrogen ion comes first. That's a monoprotic acid. If it can donate two, such as sulfuric acid, and by the way, when we name these things, if we use the naming convention, they have to be in solution. Right? That's a diprotic acid. Um, anything 3 protons or above, well, 3 protons would be triprotic, obviously. And here's an example of a triprotic. Okay. But we can also um, combine anything diprotic and above, we can combine it and call it a polyprotic. Now, there's some acids that can donate more than 3 protons. Most of these possibilities are organic acids. They're large organic molecules that have lots of hydrogens that can be donated. Now, there's a when we talk about strong acids versus weak acids, we're not we're not defining the acid itself in terms of whether it can cause damage, right? Because you can have a weak acid that is very, very concentrated that can cause serious damage. Those are terms that are reserved for the Environmental Protection Agency and Occupational Safety and Health Administration. And they're usually defined as caustic. If it's caustic, it'll cause damage. When we speak of strong acids in terms of chemistry, we simply mean, does the molecule first donate a proton? Does it have that potential? And is it essentially 100% ionized in solution? So this reaction where you have an acid donating to water produces an anion plus the hydronium ion, we're saying that that reaction is essentially one way. Let's see. Right? It's all that direction. That's a strong acid. And we speak of it in terms of equilibrium. Equilibrium will have a double arrow. So the reaction can go both directions, right? And if it's going this direction at one rate, like we're converting so many of these per second or per minute that way, then this return rate is exactly the same. That's equilibrium. But in terms of strong acids, there's really no equilibrium set up. It all goes to one direction. That, in chemical terms, is a strong acid. And these are examples: hydrochloric acid, hydrobromic acid, hydroiodic acid. These are all halogen based compounds. Then you have your polyatomic acids: nitric acid, chloric acid, perchloric acid, sulfuric acid. Those are all strong acids. And it's a detail that you really don't need to be concerned with, because it's not going to help you much with the TEAS test, is to understand that if you have more than one proton available, the strength of the acid is based upon the first proton. Because when this diprotic acid reacts with water, it donates one proton at a time. And that's the way we define chemical reactions where acids are concerned. One proton at a time. So then this one can also do a donation. That's if we just put it in water. That's what happens. This is the strong part of the reaction. This is a weak part. And it makes perfect sense, right? Once you have this anion, it becomes very difficult to remove the positive ion from that negative charge, right? There's an attraction there. So it's harder to remove the second proton. That makes it a weak acid. But when we're talking about at least one proton, or just one proton from a polyatomic, or if it's only got one proton, we're talking about complete dissociation. So this goes all the way to that end, and then we slow down. Weak acids. Weak acids we can speak of equilibrium in terms of weak acids like this, and the water molecule, and it's going both directions. So we have A minus plus H3O plus. So you have some of this, not much, but some of it, and then you have a lot of this. An example of this one is phosphoric acid, or hydrofluoric acid is weak acid. In terms of bases, we can speak of it in terms of bases also, except that bases, what bases do is, let's use example here. In aqueous solution, this simply dissociates into sodium ions plus hydroxyl ions. Acids have to ionize. In other words, this is a covalent compound, and you have to break that bond. But with bases, you have a cation and an anion associating with one another. When you put them in solution, they just break apart. So bases dissociate, acids ionize. And the idea of strength is the same. In other words, lithium, sodium, potassium, rubidium, cesium, all hydroxides will completely dissociate in water. Calcium hydroxide, strontium hydroxide, and barium hydroxide, they dissociate in water, but there's a catch. They're not very soluble in water. But whatever does solubilize is completely dissociated. So the idea of dissociation holds for either one. Now, our example for ammonia is a weak base. If you have ammonia here and water produces ammonium and OH, very little of it is ammonium. 98% plus is as ammonia. That's why when you open a bottle of ammonia cleaner, you get a blast of ammonia gas in your face. All right. We can express this equilibrium situation for acids using a procedure called the law of mass action. You probably won't have to remember that, but it's important that we explain what's going on here because this is how we understand later calculations, and we'll get to those in just a minute. So when you have this expression in equilibrium with A minus and H3O plus, water's a liquid. This is an aqueous solution, and these are in aqueous solution. Okay. For a weak acid, there's going to be some of that and some of this. But at any given temperature, as long as the temperature doesn't change, we can write an equilibrium expression for that equation by putting the denominators up here in the numerator and the unionized acid in the denominator. Now, we don't put the water down here because its concentration doesn't change. It's a pure liquid. Liquids and solids don't go in these expressions. All right, so that's all you need. For convenience, and you get exactly the same calculation, for convenience, sometimes we say this, HA, H plus, and A minus. Right. So we leave the water out of it. Now, chemically speaking, this is the actual reaction. But for calculation purposes, this one works fine. No problems there. So we would write it like this. Right? And you get the same value. This is a constant value for constant temperature. Okay? And this is called the acid ionization constant. And it is a constant. It doesn't matter what these concentrations are for this reaction. If they vary, this quotient will be a constant value. And it tells us something about the acid. Notice that if this is larger, say you have two of them, and the Ka for this acid is larger than the Ka for the other acid, then the larger Ka means this is a stronger acid. It may be a weak acid, but it's stronger than the other one because the numerator expresses how much actually ionized. If this is large and that's small because we use some of it, that means this is going to be a larger value. All right. The base dissociation constant follows a similar protocol. And if we, I'm going to stick to the slide. If we say the base reacts with water to produce BH plus and OH minus, or we could just say if it has a hydroxyl in its makeup, it would be like BOH, and then it produced B plus and OH minus. We write it this way because maybe that's an ammonia molecule. And we don't include water, but we do say that the cation times the anion, and these brackets mean its concentration at equilibrium, which is usually molarity, moles per liter. So these go in the numerator, and then the undissociated base goes in the denominator, and that's a Kb value. And similarly, if this is a large value, that means more of it has dissociated. Okay. um, all right. I think we discussed the concept of solubility earlier, but when we speak of salts in chemistry, we don't only mean sodium chloride, that's table salt. We don't only mean light salt, that's potassium chloride. A salt in chemistry is the consequence of the reaction of an acid and a base. So, I got my slides a little out of order here, but I think it's important that we talk about this reaction. So if we have an acid here and a base here, like that, as our examples, and then we react them, then we're going to get, this is double replacement reaction. We get this A and this B. So there's the positive and there's the negative. And then we get water, right? One hydrogen, one hydroxyl makes water. So if this is the acid, this is the base, this is a salt, and this is water, of course. And that's always the consequence of an acid-base reaction. This is chemically identified as a salt. Now, what we can do is we can take the salt, if it's soluble, we can take that salt and put it in solution, and then determine whether the solution is acidic or basic. And it depends on the origin of the A versus the B. We probably won't go into a lot of detail there because you won't need that to pass your TEAS test. The reaction I just showed you here, this is a generic. These are examples of an acid-base neutralization reaction. We are neutralizing an acid with a base, or we're neutralizing a base with an acid. Same thing, flip side of the same coin. And we get a salt plus water. All right. Now, if you take sulfuric acid and add a base to it, strong base like potassium hydroxide, you're going to use up both of those protons. Right. So this is not an issue of ionization of an acid where we talked about the first proton was strong and the second proton was weak, if you've got a base going in there to attack those protons, it's going to take both of them. So this is a neutralization reaction. And that's, chemically speaking, a salt. All right. If we can measure, we mentioned equilibrium value for some acid dissociation, but you can also have water reacting with itself or its neighbor, and it's an equilibrium. One proton transfers to the other one, and we get a hydronium plus a hydroxyl, like that, right? These are pure liquids. So if we write the K value for this, it's only going to be this side because these don't appear. It's going to be this one concentration times this one. Or we can simplify it and just write it like this. We get the same results. And we give this value, this equilibrium value, a special subscript, W. Water is the only compound that has that one. And when we measure it at, it's about 22.5 degrees Celsius, close enough to room temperature, we get 1.0 times 10 to the minus 14. That means that it's basically over here and very, very, very little of it over here, right? Very small values. So how, if you're working from here and you're going to there, what would be the concentration here? If this is 10 to the minus 14, then each one of these has to be 10 to the minus 7. Right? 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. So this solution is neutral. It has the same concentration of hydrogen ions as hydroxyl ions. If we put an acid in here and we unbalance it, then we're favoring an increase here and a decrease there. Then we get an acidic solution, right? Where the hydrogen ions or the hydronium ions are in excess of the hydroxyls, or the other way around. If the hydroxyls are more concentrated than the hydroniums or the hydrogen ions, then we have a basic solution. It's just that simple. Now, how would we calculate these values? Okay, I'm going to leave this down here. If we want to calculate the hydrogen ion concentration and the hydroxyl ion concentration as required for each of the following, and state whether the solution is neutral, acidic, or basic. If we have a 1 times 10 to the minus 4th molar hydroxyl, then this reaction, and by the way, this dissociation of water, this ionization of water, reacting with itself or with its neighbor, is always occurring in aqueous solutions. Always, always. No matter what else is going on, it's always there. So we can say this value is equal to the concentration of hydroxyls times the concentration of hydrogen ions, right? So it's just a simple matter of solving for your unknown. Hydrogen ions will be this one divided by that one, right? 10 to the minus 14 divided by 10 to the minus 4, which means 1 times 10 to the minus 10 molar for hydrogen ions. So right there, you can see that the hydroxyls are more concentrated than the hydrogen ions. That means this is a basic solution. All right. How about this one? 2 molar hydrogen ion concentration. 2 molar is massively greater than 10 to the minus 7. That's acidic. We could do this calculation, but it wouldn't have a whole lot of meaning. We just know that 2 molar hydrogen ion concentration is super concentrated and it's probably dangerous. Actually, 2 molar hydrogen ions is about stomach acid, right? And it would be corrosive. It would damage your skin. All right. Now let's move. We've acids, bases, salts. Now let's move to pH. What do we mean by pH? And you may have seen this term in your biology courses or even your anatomy and physiology courses, but I'm going to explain it from a chemist orientation. A Danish scientist by the name of Sorensen was working with small concentrations of acids in biological systems. Actually, I think he was working with ionized. He was working with electrolytes in solution, right? Small concentrations. So it wasn't necessarily biological. Anyway, he grew tired of having to express his terms, his concentrations, with scientific notation because all the concentrations were very low and the calculations were unwieldy. And back then, all you had was paper and pencil. So he came up with this logarithmic transformation of the values, which would give him a single number. And he said, if I know what the hydrogen ion concentration is, and I'm going to substitute hydrogen ions for hydroniums, works exactly the same way. He says, I know what that concentration is. If I take the log of it, the common log, which is base 10, right, and it has scientific notation, then part of that expression is easy. Like 10 to the minus 7th, the log of 10 to the minus 7th is minus 7. Okay. So, for example, if we say the log of concentration of hydrogen ions in pure water, right, that would be molar, then we would get minus 7. But he was averse to negatives also. So he just put a negative out here. That makes this positive. So now, and he called this pH. Small p, big H. If you write this or this, those are both wrong. Understand? Small p, large H. The general pH range that is useful, actually, we don't even go down to 0 anymore. It's greater than 1 and less than about 13. Okay, so if we want to calculate the pH for these solutions, this is the hydrogen ion concentration. So the negative log of that value is 4. The pH of this solution is 4. If we want to do it for the hydroxyls, then we would have to change the hydroxyl. We would say, all right, if it's 0.04 molar hydroxyl, what is the hydrogen ion concentration in that solution? And we would use our equation for water. Okay? And we would find that the hydrogen ion concentration is 10 to the minus 13. Then we could take the negative log and find that it's 12.6 pH. Notice that this is acidic solution. This is a basic solution. The more acidic, the smaller the positive number of pH. The more basic, the larger the positive number of pH. Anything above 7 is basic. Anything below 7 is acidic. All right. If we know the pH of a solution, can we determine the hydrogen ion concentration of that solution? And the simple answer to that is yes. If this is the expression for pH, and we know that the pH is 5.85, then how would we solve that? You have to know how logarithms work. First of all, we got to get that negative over here. You can't resolve this equation if the negative is on that side. So we would say the log base 10 is equal to negative 5.85. And then understanding how logarithms work. This value is the power of that base. 10 to the minus 5.85 is equal to that value. So hydrogen ion concentration then is 10 to the minus 5.85. Right? That's known as the antilog. On your calculator, you will have a key that says log, L-O-G. That's the common log. And then right above it, a function, press the function key, right above it will be 10 to the x. That's the one you use for this. So if I put in 5.85 and change the sign and then go 10 to the x, I get, let's see, 1.4 times 10 to the minus 6 molar. All right. Now, it's the interesting thing about logarithms. If you're trying to be correct with your significant figures, if this number has two significant figures, then the pH, or this logarithm, will have two decimal points. Right? So two significant figures, two decimal points. That means if you go the other direction, two decimal points means two significant figures. That's the nature of logarithms. All right. So I mentioned this before. pH equal to 7, that's neutral. Greater than 7 is basic. Less than 7 is acidic. These are some common values. Doesn't give you stomach acid, but stomach acid is between 1 and 2. If you eat an Italian meal with lots of tomato sauce, it's probably going to drop down to 1. There's neutral. It doesn't give you. You may have learned, if you had pH in anatomy and physiology, you may have learned the pH range for blood plasma. So pH of blood, if it's being properly controlled by your body, is between 7.35 and 7.45. Very narrow range. And we're going to talk about that in just a minute when we discuss buffers. Okay. So pH is simply a log transformation of a number. So we can do the same thing to other concentrations as well. Right? If we have the hydroxyl ion concentration, we can take the negative log of that. And what's that going to be? That's going to be POH. All right? We can do it for the acid ionization constants also. That's pKa. All right? Now, if we take the equation for the equilibrium constant for water is hydrogen ions times hydroxyls equals 10 to the minus 14. then we can use the information that I just gave you to transform this entire equation. Kw equals that times that equals 1 times 10 to the minus 14 molar. Okay. If we take the negative log of everything in that equation, this is what you get. All right. Negative log of Kw equals negative log of hydrogen ions. And when you take the log of a product, the log of A times B is equal to the log of A plus the log of B. So that would be a negative log of hydroxyls. And then the negative log of this one is 14. All right. So this negative log would be pKw. This would be pH. And this would be POH equals 14. Now, this simplifies calculations a whole lot. If we have a hydroxyl ion concentration and we want to find out what the pH is, we just calculate the POH, subtract it from 14, that gives you pH. It's just that simple. So what's the pKa for this one? Hydrofluoric acid has a Ka of 6.8 times 10 to the minus 4. We just take the negative log, and it has a 3.17 pKa. Now, what does that actually mean, the pKa? Well, if the pKa is getting smaller as you work your way through a sequence of different acids, if the pKa gets smaller, those are stronger and stronger acids. If the pKa gets bigger, it's weaker and weaker acids. So we can easily compare different molecules, different acids, using their pKa's. It's a lot easier, a lot simpler than using the Ka's. Okay. So one last word about salts. We talked about salts already. When you put a soluble salt in solution, it goes through a process called hydrolysis. And that's the case where the salt dissolves into cations and anions, and water molecules react with either one to produce hydronium ions, hydroxide ions, and sometimes both. Okay. Buffers. We can think of buffers in a whole host of different ways. We're going to talk about buffers in terms of chemistry. So a buffer in chemical terms is any aqueous solution that contains substances in it that when they react with which at a given pH, if we add acid to it, the pH will only decrease very slightly. If we add a base, the pH will increase only slightly. It stays within a narrow range. That's a buffer range of pHs. Typically, not always, but typically, a buffer is composed of a weak acid and its conjugate base. Right? So if we have something, let's take a weak acid, say, acetic acid, right? Vinegar. In aqueous solution, it will change, it will ionize into that plus C2H3O2 minus. Okay? This is a weak acid. So most of it is over here. if you just put the acid in solution. But if we add some hydroxyl to it, right, the hydroxyl then will react with the hydrogen to make water and pull the equilibrium that way and produce more of this. Okay, so at a certain point, we have a substantial amount of this and a substantial amount of that in solution. And when you have the right amount, you have a buffer. Now, what happens? Buffers contain these two active chemical species, this one and that one. So, what happens when we add an acid? If we add an acid, right, which way is the reaction going to move? It's at equilibrium now, and we have increased this amount. So there's more of it to react with this one and shift back this way. Well, what does that do? That consumes some of these hydrogen ions, and they're responsible for pH. So if we put that in there and we think the pH is going to drop, it won't drop much because we're going to use some of it up, because this is a weak acid, and weak acids always produce strong bases. This is a strong conjugate base. Okay? So it's more than happy to pick up hydrogen ions when it finds them. Right? So you're going to react this with that. It's going to go back over here, and you're going to stabilize the pH within a very narrow range. Now, what happens if you add base? Well, if we add hydroxyl ions, the hydroxyl ions are going to react with the hydrogen ions, right? Or you could say they're going to react with this acid and strip a hydrogen ion off of it, which is essentially the same thing. And you're going to produce water. So we add hydroxyl, but it's being consumed by reaction with hydrogen ions and producing more of the acetate ion, right? So that's why buffers hold their pHs close to a certain value. And this slide is everything that I just told you, right there in colored letters. Again, what happens if you add an acid? Okay. There was a scientist who his name was Henderson, and he was active prior to Sorensen's development of the pH transform. But he wanted to modify the equation for an acid so that he could calculate the hydrogen ion concentration, because that would tell him something about the acidity, the concentration of hydrogen ions in solution. So he took this equilibrium, right, the expression for the acid ionization constant, the Ka, and he rearranged it. And he said, this is my equation. This is Henderson's equation. So if he knows the Ka of his acid here, and he rearranges it, then he has the ratio of the acid to the conjugate base times its Ka gives his the hydrogen ion concentration. Well, when Sorensen came up with his transformation, another scientist by the name of Hasselbalch came along and said, well, why don't I take Henderson's equation and do a Sorensen transformation to it? So he just took the negative log of the hydrogen ions, the negative log of the Ka, and the negative log of the ratio. And he left the ratio alone because he thought it was more useful to leave it as that. So he had pH here, he had pKa here, and he had the negative log of the acid over the conjugate base. Well, we don't like that negative sign. It's too easy to get mixed up. So we changed it. What happens when you change the sign of a log expression? The quotient flips. So if we change it to a positive, now we've got the conjugate base on top and the acid on the bottom. This is the Henderson-Hasselbalch equation. And this is an extremely useful equation because it tells us something about the acid and its buffer ability. Notice that if we want a pH of a certain range to hold it there, the best way to get there is to have a ratio of conjugate base to acid that cancels out this term, and then the pH equals the pKa. This is a particular buffering system. Will have any pH of a buffered system will have the same ratio of conjugate base to acid. Now, if you have a lot of conjugate base and a lot of conjugate acid, then it has a very high buffering capacity. You can add a lot of acid or a lot of base. If it has a small concentration of conjugate base and conjugate acid, then you can only add a small amount of acid or base. That's a low buffer capacity. But they will both have the same pH. So what's the pH of a buffer solution if you have 0.45 molar acetic acid and 0.85 molar sodium acetate? All right, here's the thing. Sodium acetate dissociates in aqueous solution to produce this. So if this is 0.85 molar, that's going to be 0.85 molar. There's your conjugate base. We put it in a solution this time. Instead of neutralizing the acid, we just made it from the start. We put in that much, and then we put in the acid at that concentration. So these are our starting points: 0.45 molar acid and 0.85 molar conjugate base. And the Ka is 1.8 times 10 to the minus 5. Right? So the calculation becomes the negative log of the Ka, because we weren't given the pKa, we're given the Ka. So we have to calculate this term here, and we have to ratio the conjugate base with the acid. And when we do that, we find that the pH of this solution is 5.02. See how much easier that is than going through an equilibrium calculation, which we didn't do here, but trust me, you don't want to have to do that. If you can use the Henderson-Hasselbalch equation, it's much simpler. Now, definitions. What's an electrolyte? An electrolyte is operationally defined. An electrolyte is a substance, when you put it in an aqueous solution, the solution will conduct electricity. Right? So in this solution, we don't have an electrolyte. Whatever we put in there, sucrose or glucose, does not ionize, so it will not conduct electricity and light the bulb. However, if we put an acid, a base, or a soluble salt in there, we have mobile ions to complete the circuit. That's an electrolyte by definition. Weak electrolytes, however, don't make a strong light. They make a weak light because they don't produce as many ions in solution. Now, when we're doing a titration between an acid and a base, let me see if I don't remember if I put no, I didn't. Okay, so let me draw you a titration curve. If you have if you have a certain amount of acid here, you start off with the acid and you want to add the base. Just say sodium hydroxide. What are we going to get? We're going to get the salt plus water. Right? We're going to be consuming acid. And the pH is going to start off, before we add any base at all, we're going to start off at a low pH. And we're going to come up here to this range, and then it's going to flatten out for a while, or a very gentle slope. This is the buffer zone. Notice the pH doesn't change much. What that means is we've got HA and A minus together, just like before. That's our buffer zone. When we consumed most of the acid, then the pH is going to start going up, because now we don't have enough acid left to buffer the pH as we add base. So it's going to go up like this, and then it'll flatten out. Okay? So that midpoint right there is the equivalence point. That's where hydrogen ions equal hydroxyl ions. Right? We added the right amount of base to consume all of the hydrogen ions. So we've converted these both into water. That's the equivalence point. Now, if you have 100, 200, 300, which I've done before, of these titrations to do in a day, you want to do them quickly. And with this arrangement, you could find out the equivalence point for every sample. You'd need a pH meter, right, with a probe that goes in there and tells you what the pH is as you add base. And that gives you this curve. But that will take, if you're good, 15 minutes each, or maybe 10 minutes each. And if you got 100 of them to do, then that's 1,000 minutes, which is more than a day's work. If, however, you know where this equivalence point is located, and you can add a small amount of a compound that will undergo its own acid-base reaction, but won't significantly interfere with the primary reaction. But when it gets to this point, it changes color. And in this case, we changed from a yellow to a violet. Then you can do this titration much more quickly. If all you want to find out is where is that point, what volume gives you that point. This is when we use an indicator like that, this tells us the end point. You want the end point, or the pH at which the color changes, to be as close to the equivalence point as possible. Okay. If we're going to titrate sulfuric acid with the sodium hydroxide, how many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar sulfuric acid to reach the endpoint? All right. If we're going to reach the endpoint, then you need to know the reaction that's occurring. In this case, sulfuric acid, these are all aqueous. Sodium hydroxide produces what? Sodium and sulfate. Well, sodium is a +1 charge and sulfate is a -2 charge. So we need 2 of them. And that's an aqueous solution, plus water. Okay? So if we need 2 sodiums, that gives us 2 hydroxyls and 2 hydrogens, gives us 2 waters. So there's the balanced equation. Now, if we know that we have 1 liter times 0.5 molar, remember molarity is equal to moles per unit volume. So if you want to know moles, you multiply molarity times volume, right? So molarity times volume equals 0.5. Well, I left out some zeros. Moles of H2SO4. Well, for every one of these, it takes 2 of those, doesn't it? So we need twice as many moles of sodium hydroxide to neutralize these. So that means this is going to be 1 mole of sodium hydroxide is required. Okay. Now there's a formula that works for this. And before I use the terms, let me see if I'm going to define them first. No, I'm not. Okay. This is the best way to approach it. I think rather than give you the this other formula. Well, you might need it. So let me give it to you. If you have a monoprotic acid and a monohydroxyl base, then you can say that the molarity times the acid times the volume of the acid equals the molarity of the base times the volume of the base. That only works if you have exactly the same number of molecules here as here. This one has 2, and that one only has 1. So this wouldn't work. Not in this case. So what we have to do is modify that. You can do it 2 ways. You can take, this is 1, and this is 2. Right? And then it'll work. In this case, since we're working with a monoprotic acid and a monohydroxyl base, we can calculate the unknown. All right. That's a lot of information. But hopefully it'll get you through your TEAS test.